Alrighty, so here is the warm-up for today. If you want to do a warm-up, it wants you to solve this equation 3 different ways, by graphing, factoring, and using the quadratic formula. So if you type it in your calculator and graph it, you can just sketch your graph, use factoring, obviously move the 10 over and do the x factor, and then by quadratic formula. So negative b plus or minus square root b squared minus 4ac all over 2a. So if you would like to pause the video now and work on that before you start your notes, go for it. Okay, so topic 2 for Unit 11 is equations of exponential functions. So a scientist began collecting data regarding the amount of bacteria found on a door handle at a local school. The data in the table shows her findings as she tested the bacteria every hour. So time 0, in other words, when she first started testing the door, there's 10 bacteria units. Then after an hour, there's 20, 2 hours, there's 40, etc. So we're going to start by graphing these on the graph. Connecting them. It says, what type of function does data up here represent, and how do you know? Well, you can kind of guess what it represents just because of the unit we're in, but I do want to point out that this looks like half of a quadratic, right? We talked about that yesterday in our notes. But we know it's not a quadratic because of the common ratio, because we're multiplying by 2 over and over and over, okay? So this is exponential. How do you know the common ratio? So then it says, can you write an equation to represent this data? Well, I'm going to give you just a second, and I want you to try to write the equation. And what we are talking about is not a recursive formula. Obviously, recursive formula, a sub n, would be OH times 2. But I want you to actually write an equation, y equals, where I can plug in any number and get out any number, and I don't have to keep relying on the number before. So if you really want the challenge, feel free to pause the video and try to figure it out. I'll give you some time, but then I'll tell you what it is. Okay, the formula is actually y equals 10 times 2 raised to the x power. Okay, you may have saw that yesterday on some of our notes equations. The exponent is often the x, or is always the x in an exponential function. So in this case, our equation is 10 times 2 to the x. So just to recap, this is how many bacteria were initially on the door? 10. And then at what rate is the bacteria growing? Well, it was times 2 times 2 times 2. So you may see my formula here, 10, there's the 10, 2, there's the 2. So while there is no parent function of exponentials, the equation is created by using the y-intercept for a, or in other words, the initial value, which you can find in a table. You see this red circle right here. That would be our y-intercept, our a. And then also by using our growth rate or common ratio. You could say rate of change, but usually that's more aligned with slope. So I'm going to say growth rate. Okay, and again, that's shown over here in these green arrows. So for this table that's up here, it'd be times 3, times 3, times 3. Okay, so every equation should fit this format, unless it's transformed, but you're not going to do that until algebra 2. So you just want to plug in the y-intercept and then the rate at which it is changing. So let's practice. On number 2, here is the y-intercept. So y equals 2 times. Next is the rate at which this is changing. Well, this actually isn't growing, it's decaying, it's getting smaller. So if it's hard to tell right off the bat, you kind of look a little bit further. 8 to 2, for example. Some of us think of that as dividing by 4, but we're going to write times a fourth. That also applies here, and really it applies at the beginning and at the end. So in parentheses here, I'm going to have a fourth raised to the x, and that's my equation. Okay, the next one, here's my y-intercept, so now let's look and see what the change is. Well, that's times -1, but that's not times -1. And that's not times -1. So I'm going to look for a different change here. This is actually -2, -2, -2, -2. Well, what did we talk about yesterday? What does that represent? This is actually a linear function. So just a random linear thrown in here just to kind of keep your brains fresh. So if I'm trying to write a linear function, we like to go back to y equals mx plus b. So in this case, we'd have y equals -2x minus 3. Okay, but continuing on with exponentials, no more tricks for you. On number 4, here's our y-intercept. So y equals 27 times. Now we look for the rate of change. So we're going from the y's here. 3 to 9, 9 to 27, 27 to 81. Those are all times 3's. This would be times 3 to the x. Try number 5 on your own. Pause the video. Okay, hopefully you got y equals 3 times 1/2 to the x. Now, I would suggest you put the 1/2, or any fraction really, in parentheses so that we know that it's the entire fraction raised to the exponent. If you were to just write it like this, it might look like it's just the 1 that has the exponent and the 2 doesn't, which would be incorrect. So I'd put any fraction in parentheses. Okay, so let's try some word problems. It says black mold grows at an alarming rate. It can double in size, that's important, over the course of a week. Write an equation that would model the amount of black mold in a house after X weeks, assuming there are currently 300 particles of mold. So, writing an equation, y equals currently, or initially, we're at 300, times, if it can double in size, that means it's 2 to the x. So then they want to know, how many particles of mold would there be after 6 weeks? Well, that means we want to work out y equals 300 times 2 to the x. We talked about yesterday using your calculator to do that. You can just type that into your run matrix menu. 300 times 2 to the 6th power. Okay. If you're watching this in Miss Sable's room, or, well, actually anywhere, because STAR testing is going on, you probably don't have a calculator, so I'm just going to be telling you the answers today, but just know that you will be expected to do this on your calculator on your own on a quiz or a test day. So this actually ends up being 19,200. How much would it be after a year? Well, that would be 300 times 2 to the 52 power, because it's weeks. Our answer is actually something in scientific notation. 1.351 times 10 to the 18th power. Which, remember, that means that we would move this decimal point 18 times to the right before we get our actual standard form answer. So it means that is a ginormous number. It's going to have 15 zeros after it. So I don't even know what you call that, but it's a big number. So then how long would it take for there to be 1 million mold particles? Well, that's working the other way. That's giving you y, and then asking you to work backwards to get x. This is what you do in the graph screen when you do the xcal function. And your answer here, you get 11.7, so we'd say 12 full weeks. Okay, again, I apologize, this is kind of bad timing for you not having your calculators. Okay, number 7. Miguel wants to work on his arm strength. He plans to make a push-up plan that will help him achieve the arms of his dreams. If he does 2 push-ups on day 0, there's our initial amount, and then plans to double the number of push-ups he does every day after that. Write an equation that represents the number of push-ups y he does on any given day x. So we've got y equals 2 times, well, if he's going to double it after that, it'd be 2 to the x. So 2 2's in this case. So now they want to know how much we'll be doing after 1 week. That's just 7 days. So I'm going to plug that in. Y equals 2 times 2 raised to the 7th power. So just 1 week later, if he follows his plan, he will be doing 256 push-ups, which is a little bit insane. So he may want to rethink his plan. Doubling things gets really high really fast. Okay, 8 and 9, very similar. Again, they just want us to write these equations. Well, if we're following this model, where A is the y-intercept, we just look at our graph. So for this first one, it's at 100. For the second one, it's at, ooh, that's hard to see, -3. So then the B is the rate at which it's changing. Well, we go from a 100 down to a 50, down to a 25. Well, that's being cut in half over and over. The second one, we go from -3 to -6 to -12 to -24. Excuse me. Even though these numbers are getting smaller and smaller, we really are doubling the number. If you make a table, for example, you think about going from -3 to -6 to -12, etc., you're just multiplying by 2 over and over. So this is still just going to be 2 to the x. Okay, on the back, we have a little activity that if you just really want to do it, while you watch this video, you go for it. if you take a piece of paper and you start folding it, there's actually kind of an interesting fact out there that you can't fold a piece of paper more than 7 times. No matter how big or how small that piece of paper is, it is impossible to fold it more than 7 times. Maybe it's 8 times. I don't know. We'll have to look it up. But there is an interesting fact out there. Go Google it. So if we were to try this, if you take a piece of paper and you don't fold it, there's just one layer of paper. If you were to hold it up at eye level, you just see one layer of paper. And you would have a whole piece of paper in front of you. If you fold it once, picture yourself folding it like hamburger style, and then looking at it sideways, you'll actually have 2 layers of paper there. If you open it back up, your paper is then cut into half. Okay, think about every time a teacher's asked you to make a foldable. You fold things and you have those little crease lines, you'd have half the paper on each side. So if you were to take that and fold it again, you would have 4 layers of paper, and your paper would be cut into fourths. You kind of see the pattern here. 3 times would give you 8 layers, and you'd have 8ths, then 16 and 16ths, 32 and 32nds, 64 and 64ths, etc., etc. Okay, so they want us to plot the points from the left-hand side of this table on the first graph, and then the right-hand side on the bottom graph. So 0, 1, 1, 2, 4, 8, 16, okay. We're starting at 1, going down to a half, a quarter, etc. from there. Alrighty, so if you fold paper 18 times, how many layers of paper will you have? Well, we need the equation to do that. So going back up to this table, this box right here, if we're talking about x times, will be represented by just 2 to the x, because our initial value here is 1, so really it'd be 1 times, and then this is just doubling over and over, so 2 to the x. But I don't really need that 1 anymore, so just y equals 2 to the x. The right-hand side, same thing. My initial value is 1, and then I'm cutting it in half over and over, so y equals 1/2 to the x. So using that formula, I can answer these questions. So 18 times, how many layers? That'd be 2 to the 18th. Again, you don't have your calculator, so let me just tell you. 262,144 layers of paper, which is kind of bonkers. Think about folding something 18 times. That doesn't sound like that much. But if you think of 262,000 layers of paper, that's literally like 262,000 pieces of paper stacked up. It'll be super tall. So number 5, a box of paper is 5 reams of paper deep. A ream of paper has 500 sheets of paper in it. So that means you picture a box, and it's got 5 reams in it, and each one is 500. That means this box is, how do you use the math there, 2,500 sheets tall. So know how many folds would you need to make one piece of paper as thick as a box? So this is one of those cases where we're setting our equation equal to a number, and we would have to use that xcal function in our calculator. Again, I'll solve it for you. The answer you get is 11.28. Something. I guess it's really 11.29. So you can't fold it 0.29 times. So you'd have to fold it 12 times, and that one piece of paper would be as tall as a box of paper, which is weird to think about. Okay, number 6. If you fold paper 9 times, what fraction of the piece of paper is each region? So that is using the 1/2 function. I'm going to put a 9 up there. Again, let me do it for you. You get 1/512. So again, only folding it 9 times separates your paper into 512 pieces, which is crazy. Last one, your school has a paper confetti machine that cuts 8.5 by 11, that's just normal paper, into about 400 pieces. What is the least number of times you would need to fold the paper to get regions that are no larger than 1/400th of piece of paper? So again, what they're saying is your school has a machine that takes a normal piece of paper and cuts it into tiny little pieces like this until you have itty-bitty pieces of confetti. So they want to know, if you were to do the same thing but folding it to get that many regions, how many times would you need to fold it? So they're saying 1/400th equals 1/2 raised to the x. So again, you'd use your calculator in the xcal, and you would get let's see, 8.64. So you would have to fold it at least 9 total times to get that many little bitty pieces of paper shown on your bigger paper. Okay, so just to recap, what's important from this topic is really the fact that every exponential can be written in this form. This is your y-intercept, or your initial value, like your starting point. And then this is the rate at which it's changing. So in most of them, we could call it a common ratio. Sometimes it's how fast it's growing, sometimes it's how fast it's decaying or getting smaller, but it's really the number you multiply by. Okay? So there is a homework assignment in Schoology. It's not due tomorrow because you have STAR tomorrow. We want you to focus on that and getting good rest. But if you have plenty of time in class left, go ahead and work on that. Try to get it finished. If you don't, it'll be due on Monday. Hope y'all have a great STAR tomorrow. Good luck, and I will see y'all on Thursday.